Hello friends, this video on isolation of elements part 9 is brought to you by examfear.com. No more fear from exam. So let's talk about the electrochemical principle of metallurgy. See, till now we have seen that thermodynamics is applied for metallurgy, right? So we have seen that in thermodynamics we have some metal which some power, we reduce it to metal. For example, FeO, we reduce it to Fe. Right, this is +2 charge, this is 0 oxidation number. So we have used thermodynamics principle to reduce metal. So to reduce metal we have used something called reducing agent, and typically we have used coke as the reducing agent. Actually we can also reduce the metal oxide by supplying electron. For example, in this case you supply 2 electron, it will become metal 2 plus with 2 electron will become metal. Right, so by electrolysis we can do, if you see the Faraday law, delta G is nothing but minus NF E naught. So N is the number of electrons required. For example, here you have 2 charge, so 2 electrons are required to reduce. F is my Faraday constant, and E naught is my electrode potential of redox couple. This is electrode potential of redox couple. So the delta G we can also supply using this charge, and that's why if you add electron you can actually reduce the metal oxides to metal form. Correct. So here there is a reactivity series. We have discussed this in the chapter, electrochemical chapter, I think. For example, you have copper is a better copper will be reduced earlier. For example, you have copper plus and iron, the output will be copper and iron plus. So here iron is oxidized and copper is reduced, right? So the less reactive metal actually come out of the solution. For example, in this case copper is less reactive than iron. So if you have a solution where you have some, for example, you have copper sulfate and iron, so in this case the less reactive is copper, so copper will come out and iron will become iron sulfate, right? So more reactive metals have large negative values of electrode potential, so their reduction is difficult. Please note, see the reactive, when I say the reactive, more reactive metals, that means that the metal will not be in the form of pure form. Example, if let's suppose metal M is reactive, that means metal will be in the form of M plus with some charge, because it is reactive. Since this is the favorable state, if M is reactive, so that means it is difficult to reduce M plus some N to M if it is reactive. Correct. So just think from this perspective. It is a reactive metal, they will have tendency to be in the form of M plus N state. If it is a non-reactive metal, it will be in the have tendency to be in the normal state. For example, gold you will find more gold in the Au state than Au plus 2 state. You will find more gold in this, right? Similarly, zinc you will find in generally in Zn2 plus state as compared to gold. So think from that perspective. Even if you don't remember the chart, just think, if it is a reactive metal, it will try to be in this form. If it is a non-reactive metal, it will try to be in the normal form. So in this case, precaution has to be taken considering the reactivity of the metal produced, and the suitable material has to be used for electrode, because here we use electrodes. These are my electrodes. We have discussed this kind of process, electrochemical process, in the last few chapters, so I will not discuss more on this. But we have electrode, we have a power supply, positive charge, negative charge, and when we are doing this, when we are creating metals, so in this metallurgy process where we are using the electrochemical process, you have to make sure that the electrodes and this metals don't react. right? Sometimes even, since it's all about current here, and this solution, the molten metal may not be conducting, may not be that much, that good conductor, so we add some flux. Sometimes we even add some flux to it to make sure that the molten metal is more conducting. So we'll discuss about these when we take some specific examples. For example, we'll take the electrochemical process of metallurgy, where we try to extract aluminum from aluminum oxide. So in this case, what we do is we have this kind of container, and here we have Al2O3 that is mixed with Na3AlF4, or we can also use CaF2. Why this is used is, this actually lowers the melting point of mixture, point of this Al2O3 mixture, and the second thing is it brings more conductivity. As I told, the molten metal, whatever you have, it has to be conducting, right? So we mix this with Na3AlF4 or CaF2. This makes it, this decreases the melting point and also brings more conductivity with the whole solution. And in this, if you see, there's a cathode, there's an anode, and there's a steel cathode and the graphite anode. This is my anode, and this is my cathode. So if you see, this is my anode. Anode is place where oxidation takes place, and this is my carbon, graphite. So here carbon is converted into CO, right, plus 2 oxidation state, or CO2 in plus 4 oxidation state, right? This is CO and this is CO2. So here you see the oxidation of carbon take place, and this is anode. Similarly, the cathode is typically steel, and the whole process is called Hall-Héroult process. So in this process, what happens is, this is my Al2O3. So Al2O3 now reacts with carbon to form aluminum and carbon dioxide gas. So if you see, carbon is getting oxidized and aluminum is getting reduced. So with this, since aluminum is heavy now, aluminum comes in this part, since aluminum is heavy, and aluminum can be collected here. Correct? Note that for every 1 kg of aluminum produced, you need almost half kg of this carbon. So this is, if you see, it's almost detached, right? You just keep on changing it. You use this carbon is, you use this anode, carbon is exhausted. You change the plate, you add more and more carbons, right? So if you see the typical reaction at cathode, this place cathode, this is my cathode. So cathode, the reaction that happens is, my aluminum, Al2O3, aluminum is in +3 oxidation state, it becomes Al, and it takes 3 electrons from this battery. Similarly, if we talk about the anode, where oxidation is taking place, we talk about the reactions at anode. So carbon will react with oxygen with -2 state. It will form CO and it will give 2 electrons. Similarly, carbon will react with oxygen, 2 oxygen actually with -2 state. It will form CO2 and 4 electrons. That means carbon goes from 0 to +4 or 0 to +2. So 2 of these are possible. These are my anode reaction, and this is my cathode reaction. Correct? So this is a process to extract aluminium from aluminium oxide. If you see aluminium oxide, we are actually doing nothing but we are reducing aluminium oxide to aluminium. But instead of using a thermodynamics process where we use some reducing agent, what we are doing is we are using electrical power. We are using electrons to reduce aluminium oxide to aluminium. The next is copper. So we get copper from the low grades copper ore and scraps using this. So let's suppose this is a low grade copper ore. Low grade copper ore. Correct? And this is the output actually. This is the copper. I'll say not say pure copper, but it's copper. So what happens is the low grade copper ore can be extracted using this method. So low grade copper ore will be also in the form of oxides or sulfides, Cu plus 2. And we are using some acid here. So this will become Cu and you get H plus here. So here if you see reduction of copper, oxidation of hydrogen. So if you see this animation, this from this copper plus 2, because we had Cu2 plus, it gets the electron. This is anode. Actually there is a issue with the sign. This is a negative charge and this is a positive charge. This is anode and this is cathode. Why cathode? Because cathode where reduction take place. So here I had Cu2 plus, this is a ore. This is not copper, this is a ore. Maybe Cu2O or Cu2S. This ore is getting reduced to copper. Right here. Correct? And in this position anode oxidation is taking place actually. So here my hydrogen is getting converted into H plus. And if you see, end of the day all the impurities will settle down. So the question is, at a site low grade copper ores are available and zinc and iron scraps are also available. Which of the two scraps will be more suitable for reducing copper ore? So we have to choose between zinc scrap and iron scrap. Between these we have to pick and we have to reduce the copper ore to copper. So if you talk about the zinc and iron, which is more reactive? Zinc is more reactive than iron. Zinc is more reactive than iron. This is something we know. Correct? Why zinc is more reactive than iron? This is something we can know from the electrochemical series. Zinc is above iron. If zinc is more reactive than iron, and zinc will be happy to stay in this position. That means it is easier to oxidize zinc. That means zinc is a good reducing agent. Right? If zinc get oxidized, zinc will reduce something else. So zinc is a good reducing agent. When you compare zinc and iron, zinc is a better reducing agent as compared to iron. Right? So in this case, what we have to do, we have to reduce, right, copper ore to copper. So this is in copper 2 plus form, we have to reduce to copper. So zinc is a better option. But if you talk from the industrial perspective, cost is also a factor. Zinc is costly than iron. Zinc is costlier than iron. Zinc is costlier than iron. That means if we talk from the cost perspective, it is advisable to use iron scraps, right? Because it is cheaper and cost plays a role here, right? Since it is cheaper, we can use iron here. It is advisable to use iron here. Correct? Next is oxidation reduction. That is also used to extract non-metals. Generally, this is used to extract non-metals. See, non-metals are extracted by oxidation. For example, extraction of chlorine from brine. Brine is NaCl, widely available, seawater, the ocean water. So we have plenty of this NaCl, that is brine, from the seawater. And what we do is NaCl is nothing but Cl minus. When you react with water, it gives OH minus and hydrogen gas and chlorine gas. Right? So delta G for this is reaction is plus 422 kilojoule per mole. That means it won't happen on its own. For this, you have to supply some energy. That is delta G is minus NF E naught. So what is the value of N? N is 1. And F we know is Faraday volt. E naught is if you give E naught as, if you put the values right, E naught comes out to be 2.2 volt. That means if you supply 2.2 volt in this NaCl solution, you will get chlorine gas. How? See, delta G is 422 kilojoule per mole, so that means this energy has to be supplied from some external source. And currently we are using electrolysis here to do the oxidation reduction reaction. So that means this energy has to be supplied from the electrons. And the same formula you can use is delta G is nothing but minus NF E naught. N is 1 here because chlorine goes from -1 to 0 state. F is Faraday constant, you know the value of that. So we put the value and we get E naught as 2.2 volt. This oxidation reduction concept is also used for the extraction of gold and silver. Extraction of gold and silver. We have told you this in the leaching. In the leaching, for example, I have a gold, then I will use a Cn minus as my leaching agent, and within the presence of water and oxygen, what you get is complex compound. Right? This is leach now. Now this, actually, we have to use some reducing agent now. So with this you get gold back. And what you get is ZnCN4 2 minus. So here if you see, we are using some reduction and we are using some oxidation also. Right? So we are using both oxidation and reduction here in this process also. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.